Hello everyone. We want to continue on the topic of relative permeability, and we discussed the relative permeability curves for imbibition process. Remember that imbibition process is the process at which the wetting phase saturation increases during that process, and drainage process is a process at which the saturation of the non-wetting phase increases during that process. Now, you see two figures here, and one of them is for a strongly water wet rock, one for a strongly oil wet rock. And as you expect, for the water wet rock, basically you will have lower values of relative permeability curves, and you see the relative permeability values goes all the way up to maybe 15% at 80% water saturation. That's due to the fact that the water sticks to the surface of the rock and doesn't really move a lot. And in the case of strongly oil wet, the water have more freedom to move, so this curve becomes kind of more steep compared to this one. And at around maybe 70% water saturation, which is less than what we had in the case of a water wet rock, the relative permeability is actually higher and reaches to a number around 80%. Also, if you look at the intersection between these two relative permeability curves, you see that since the water have more freedom, the curve basically moves a little bit upward, and the intersection of these two curves becomes at a point which is less than 50%. So if you see basically the relative permeability curves that the intersection of these two lines are less than 50%, then in that case the relative permeability, basically you are dealing with a strongly oil wet rock. However, if the relative permeability curve intersect at a saturation which is more than 50%, then you're dealing with a water wet rock. So next, we want to talk about different parameters that affect your relative permeability. One of them is fluid saturation. Of course, all the functions that we have discussed so far are in terms of relative permeability was related to the fluid saturations. Geometry, porous space of the pores, and what is the pore size distribution inside the rock, what type of wettability you're dealing with, fluid saturation history, imbibition or drainage. These are all the factors that would affect the relative permeability. Now the history basically brings us to a new definition and a new topic, which is called hysteresis. So hysteresis is basically in general any process that if you move forward is different from the process that you move backward in terms of the history of what's happening inside your rock, then this is called hysteresis. So for example, if you look at this figure, you see that, let's assume that you have a core sample that is 100% saturated with water, right? So it was a dry core sample, you 100% saturated with water, and now you're trying to inject the oil into the core sample. So the water saturation starts to drop, and the relative permeability of this is the non-wetting phase relative permeability. So KRNW means the non-wetting relative permeability. And you see that the relative permeability of the non-wetting phase increases because the saturation of the non-wetting phase is increasing in this case, and the process is toward that direction. You're injecting the non-wetting phase and substitute it with the wetting phase, right? So that's the process, 100% saturated with wetting phase, and you get to a point at which you reach the irreducible water saturation if the water is basically your wetting phase, right? So this number in this case is around 25, 30%. And then let's assume that you take that core sample and then you re-inject water into the core sample. Now the saturation of the wetting phase is increasing. This is called an imbibition process. Previous process was drainage because the saturation of the non-wetting phase was increasing. So during this drainage process, let me go back to that. The relative permeability of the non-wetting phase increases. The relative permeability of the wetting phase during this process decreases. and both of the relative permeabilities are, this one is at 100% here, this one is 100% at irreducible water saturation. Now if you go back, you inject the oil back into the core sample, then you cannot really get to 100% water saturation now, because you have a residual oil saturation inside your core sample. So the process is not going to overlap what you did previously, and it's going to go through this direction, and it will end up at this point because of the residual oil saturation. So this is called hysteresis, because the process forward is different from the process backward. Okay, in terms of the wetting phase relative permeability, really they do not significantly change from each other during these two processes, so they overlap each other in this case. This is called hysteresis, and this is again because your relative permeabilities are different in different directions. So here you see that again, that's the same graph, right? We discussed this. Common examples of the drainage process is petroleum accumulation in the reservoir. For example, initially you have a reservoir 100% saturated with water, and oil and gas are formed in the source rock, migrate upward into the reservoir rock or trap, and then they displace the water. If your rock is water wet, then the oil is displacing water, which means the saturation of the non-bedding phase is increasing, and therefore that means that you are dealing with a drainage process, right? So that would be the relative. You have to work with the relative. If you want to model such a process and you want to put it into Darcy's equation, you have to use the relative permeability curves related to the drainage process, not the relative permeability curves which are for imbibition. Example of imbibitions are water flooding in a water wet reservoir. Let's say you have produced from your reservoir for a long time, and then you want to inject water to produce more oil, right? If your rock is water wet, you are increasing the water saturation by injecting water into the reservoir, and that means that you are dealing with an imbibition process, and you have to use the drainage process relative permeability values to put into the Darcy's equation and model the fluid flow inside the porous media. So let's do this example here. It's a pretty simple example. You have the oil and water relative permeability curves, and we want to find the effective permeability for oil and water at a water saturation of 50%. Absolute permeability of the rock is given to be 214 millidarcies. So if you look at this problem, we're looking at 50%. So 50% is this point, right? That's the water saturation, and the first thing we get from this curve is to read the values of relative permeabilities. Now I'm going to just approximate the numbers. This curve is the water relative permeability curve, this curve is the oil relative permeability curve. So at 50% saturation, water saturation, relative permeability of water is equal to maybe 0.09, and the KRO from the other curve is around maybe 0.12, right? And we want to find the effective permeability of oil and water. So KO is equal to KRO multiplied by absolute permeability based on the equation. KRO is 0.12 multiplied by 214, whatever number that is. And K water is KRW multiplied by absolute permeability, which is 0.09 multiplied by 214. And you can get the effective permeability values. Alright, that's it for this video. We'll continue on this topic in the next video.